I'm starting the live stream. Hello, this is Maths live stream on Twitch. My name's James. This is Chill Maths, where we just try to maybe learn some maths, do some math stuff, but in a kind of chill way if we can. Hello to Herb in chat. How are you doing? Hi to anyone else who's joined us. It's the weekend. And I've got a plan. I've got a little bit of a plan. I plan to learn some maths that I think I already know or that I should know. So this has got a chance to be very embarrassing. Maths that I should know. Hi Mary, I can see I saw maths 2 in chat as well just before we went live. Good to have some people here. I think I'm going to show you what I've got. It's differential equations. The ODE up here stands for ordinary differential equation, which I now realise it says up there, doesn't it? There's an ODE. I have a pointer, that's good. Technically, I should know quite a lot about differential equations because I used a bunch of them for the sort of research that I did back when I did research, and I've done tutorials, small group teaching, for the course after this one. Occasionally, very long time ago for this particular course, but also for the course after it. So I should probably know what's in this course. And I think I generally do, but there's some content that wasn't in the version of the course that I did when I was a student, so that's a little bit different. There's some differences, and there's a big theorem right at the start with a complicated proof, which I can't remember it at all. I'm not sure if I've ever been able to remember it. I don't think I've ever learnt it for an exam or anything. So I thought I'd have a look at that and try and face the kind of embarrassing fact that there's this course about a topic that I feel like I should know about, which I have very little memory, maybe have never had memory of. Good, face the things, but in a chill manner. That's the plan anyway. Good, right, okay. So this is a second year course, which is perhaps why it's different from what I studied. When I studied this sort of thing, there was a first year course, and then we got quite specialised later on, but I didn't have a whole second year course on. I did, but it was quite different. This one is the Oxford second year course. I've got some lecture notes from a few years ago, if anybody cares. They're just Oxford has all its lecture notes online for the maths course. I've just picked up Differential Equations 1, which is the name of this course. And it's going to tell us about this stuff. So I hope you're all doing well at home. I hope you've got having a nice weekend. The plan is that I'm just going to read through this a little bit and make notes on it, and we might go off on a tangent and talk about other stuff as we go along. If you're new here, if you're joining in for the first time, then hi, great to have you with us. We are one of the only shows on Twitch where people try to learn maths together. There's a few others, but this is one of them. Need a better tagline. Right, okay, here's an ODE. And here's some questions we might ask about ODEs. I think this is fine. The derivatives depend on, the highest derivative depends on previous derivatives, and we're using this notation. I should try and remember the notation that we're using in this course. It seems to be a mix of primes and numbers in brackets, which I will have to remember. And there's also one of these over here as well. Okay, there's order in the same sense that polynomials have order, sort of. We might be able to we might be looking to solve things. Yes, that's what I would like to do. We might ask about whether it has a solution and whether the solution is unique. And that's the sort of thing that I've never been any good at. I know there's theorems for special cases of differential equations where you can say things like this, but I can never remember which ones or what you get to say. Okay, yeah, we use order for absolutely everything, don't we? Order of an element in a group, you've got order of a polynomial. Maybe you say degree of polynomial. Is that the word I'm thinking of? Yeah, that's the word I'm thinking of. Degree for a polynomial. But order can also be what people say for sorting things. To order them when you're doing permutations and combinations. You might look at the possible orderings of some things. And there's also this thing called a well order or total order, which is more to do with defining something like an inequality on a set of objects. That's a tangent. Right, okay. Here's a first order differential equation. Yeah, okay. The derivative depends on x and y. Is that what I want? I suppose that's what ordinary means. Some of the differential equations I care about have weird combinations of y's and y primes. I guess that's for another day. Yep, okay, good. Initial value problem, since we're starting with an initial value. Good. Yeah, I know how to solve some of these. Good. I might expect it to exist. Here are some difficulties. And I like this course because it has warning examples. Sometimes you see examples in maths lecture notes, because of course you do. Sometimes you see non-examples, which I like. A non-example is when they show you something that is not an example of the definition or the group of things that we're talking about. So as to give you an idea about where the edges are. I think you see this in school as well. Maybe someone says we're going to look at quadratic equations, and a quadratic equation might look like this, but not like that, and definitely not like this, and not like that either. It looks like this or this or this. So you give you some examples. Anyway, a warning example is one where I guess it's not really an example of something working. It's an example of something not working, or not behaving the way you might expect. So here we go. It's an initial value problem. There's a lot of 3-letter acronyms in this course, I think. Or at least 2 so far. That's a lot, right? The derivative of y is 3 times y to the 2/3, which I think you learned this off in school at some point, right? So if I write it like this, that's a little bit more familiar. I think you know what to do. Oh, now there's a 5 in the way, isn't there? To the power of 2/3. I think you know what to do. This is separable, so you might go and separate it. You might go and divide by y to the 2/3 on both sides. You might integrate with respect to x, which becomes with respect to y on the left-hand side. I think you know how to do this at some point in A level, and then you get a bit carried away. There you go. So y to the 1/3. Oh, and I see there was a factor of 1/3 in here as well, really. So I should multiply this by 3, 3x plus a constant or something like that. It's a test of me being able to integrate. So then you might conclude, I'm going to call it 3c instead of c, see if anybody minds about that. So then you might write down something like y is x cubed and be happy because you're now done. I guess x plus c cubed, if I don't forget my c. We've got an initial condition, which is why I got maybe too carried away there. We know that at 0, y is 0. So that's kind of something you might learn to do at A level, is to do this kind of rearranging and to integrate both sides. I think different people learn different notations. Maybe if you're doing something equivalent to A level, some of you learn totally different things to write, but maybe you can do that sort of calculation. And the point of this course in second year at university is to point out that that's not the only solution to this differential equation, and something has gone terribly wrong. That's what the warning is. We're going to see this on the next page, I think. Yeah, okay, I was doing quite well. There we go. Separate variables, which you learn in prelims or first year or even A level or whatever. Good. Okay, here's a solution, but there's another solution that just y equals 0 works back in the original differential equation. Y equals 0 just works. Because on the right, it's 0, and on the left, well, the derivative of constant 0 function, the derivative is also 0, so these things match up. That's problematic, because now we've got 2 solutions. We've got this one, which we were very happy with, and we've got that solution, which we missed. I guess we missed it because we divided by 0 at one point. And in fact, there are infinitely many solutions, because you can do this, which looks like this: x minus a cubed below a, and then 0 for a bit, and then x minus b cubed, which looks like this. So b is here, a is here, this is x minus a cubed. The 0 function, this is x minus b cubed. Okay, right, this is terrible. So this is all these weird piecewise functions also work. Which I guess you might look at and say, well, I didn't mean any of those, right? This function's got kind of corners, hasn't it? If you look closely, you realise those are not corners. That it's not really got a kind of sharp corner there, because this x cubed, I haven't drawn it very well, have I? But this x minus a cubed, as it gets in towards a, it's kind of a triple repeated root there, so it's going to be very flat nearby. Technically, it's going to have a continuous derivative and also continuous second derivative, in case you care about that. So both sides of this equation, which are just asking about the values and the derivatives, they're both fine. They're both nice continuous functions, differentiable functions on both sides. So yeah, we've got something that just sort of works. It comes down to the idea that I think we divided by 0 at one point in there. The reason that our A-level method missed some solutions is because we divided by 0. We divided here to get to something like this. We divided by y to the 2/3. Yeah. Catch up with chat. Maths to do has seen something like this in functional equations. Those are the ones with the f's in, right? Where you have some property about a function and you need to go and work out what the function is, and you find some easy solution, but you've missed some really weird solution. Is that the kind of vibe we're going for? Maybe you've got a specific example of a functional equation in mind. But sure, you can come up with ones where, oh goodness me, how does this work? I feel like I've seen something weird where, yeah, something like f of x plus 1 is equal to f of x. No, this is daft, because this is just a statement about a periodic function. Okay, not this. Hi, Rice Cooker Man. We're learning about differential equations. I'm supposed to know about differential equations, but I'm not sure I know what's actually in the Oxford courses, which leads to friction when I'm talking to students about what they're doing. And they've done one particular course, and I did a slightly different course many, many years ago. Hi, Les Jomer. Good to see you as well. So this is potentially really embarrassing for me. If my students find this and find out that the person teaching them differential equations 2 can't exactly say what's in differential equations 1, then terrible news. But hey, I'm learning. Yeah, like partial differential equations are where you might have a function of many variables, and you might want to take derivatives with respect to different variables, which kind of, I hope, makes more sense. As a sequence of words, it doesn't sound like it makes sense, but partial differentiation really is just, you've got a function that depends on lots of stuff, specify which thing you're changing, and off you go, do a kind of derivative in that direction, if you like, with respect to that variable. I mean, so long as you're just quite careful about what you're taking different derivatives with respect to, you can do all sorts of calculations like that. And they are very useful if you have big data, or you have something that depends on lots of input variables, which lots of things do these days, have large data models, whatever. Okay, partial differentiation is one of those things that people say is important for matrix stuff. All of the AI depends. That's why if you're doing linear regression, you might need to use the language of differential equations. Yeah, right. Okay. Yeah, that kind of vibe. Thanks, maths. That kind of vibe where you've got some bits and pieces, and you're looking out for these kind of piecewise things. Although I think piecewise functions get a bad rap. Hi, Neutrino. We're learning about differential equations. I think piecewise functions get a bad rap because if I take your favourite function, your actually top function f of x, and I say, well, how about this piecewise function defined as f of x if x is less than 0 and f of x if x is greater than 0, then g is kind of a piecewise function, which sometimes get a bit maligned. Like people think, oh no, piecewise functions. I think piecewise function is very scary, not good. But actually, this is exactly the same as your favourite function. It has the same values as your favourite function. It has all of the nice properties that your favourite function has, whatever your favourite function is. So really, you shouldn't be too scared of piecewise functions because maybe they're just nice. Maybe they have nice properties. I suppose that they're often introduced as a way to show you things that are discontinuous or horrible or just have some kind of horrible thing going on at that point. But I guess the example over here shows you that that doesn't have to be the case, that these piecewise functions, although it looks very scary, it's got 3 cases in here, although it looks pretty scary, maybe it joins up nicely and the derivative matches up different places. Git. Hi to who else is here? A neutrino here. Yay! Oh no, I was talking to neutrino. Right. Yes. Hi. So actually, this piecewise function is pretty nice. I would probably write it. Oh, what would I do to make this consistent? I'm just going to rewrite this slightly as y equals, and I put one of those braces for cases. We've talked about those before, I think. Okay, good. Okay, so here's a weird solution to a fairly normal looking differential equation. You might see something like this at A level or equivalent, and just find the obvious-ish solution, miss the really obvious solution, and definitely miss the weird solutions. And there's infinitely many. So ideally, we would have some sort of technique to decide whether or not differential equations are going to let you down in this way, whether they're going to have lots of other weird solutions. Because it'd be nice if we could talk about the solution. If we could say, aha, for reasons I know that this thing has a unique solution, here it is. If we could point to some sort of unique solution. And there is some maths for that to work out whether these things have unique solutions or not, which I think we're getting to. Right, okay, solution does exist, but not unique. It'd be nice if we had a warning example of the opposite, right? So in this case, the solution does exist, but it's not unique. It'd be nice if we could show you an example where the solution is unique, but doesn't exist. But sadly, is unique, doesn't exist. Sadly, that's a contradiction. That doesn't happen. It doesn't make any sense. If it doesn't exist, then there aren't any. So that's annoying. I guess we should have a look at one where there isn't a solution. Yeah, let's look at this. Let's look at this next bit of the notes, that being the concept of what we're doing today. I hope I've got figure 1.1 because I've got a big gap here and then the number 6. Page number, but okay, never mind. Yeah, so this is an example of finite time blow up. Here's a differential equation. dy by dx is y squared. So this says at each value of x, the derivative of this function is the square of the y value. Maybe you've met exponentials where the exponential function has derivative equal to itself. What if instead you looked for a function where the derivative was the square of itself? Which, if the function gets large, then this will be very large, so the derivative will be very steep. Steeper than e to the x would be at that large value of y. And in fact, this function gets so steep so quickly, it turns out to be 1 over 1 minus x. There's some separation of variables going on there, apparently. No, same idea, really, isn't it? You divide by y squared. Divide by y squared, being careful because that might be 0. I guess 0 works as a solution. Oh, it doesn't have this. Doesn't do this. So you can separate variables and integrate up. I can't talk. Separate variables and integrate up and get this thing, which doesn't exist as x gets, well, it doesn't exist at 1. I'm going to discover that's unique, but only up to a point. Some people draw the solution. So I've seen this at people starting uni, and I think later this week I'm talking to some people where I'll probably try and talk about this. So let me try and think about what I'm going to say. Sorry, I sometimes use these Sunday streams to plan what I'm going to do. We had one about planning out some Galois theory. We did an afterwards session after I'd done some stuff on Galois theory. This is probably the right way around, where I plan ahead. So what's the mistake that people make here? The mistake is something like you separate variables. Let's do the separation of variables very quickly over here. So here's the separation of variables, divide by y squared, and then put integral signs on both sides. Integral of 1 dx, again x plus c over here, and a minus 1 over y. So then something like y is, oh my goodness, I want a minus sign, plug in y of 0 is 1. So when y is 1, x is 0. So c is minus 1. Yeah, good. And then y is 1 over 1 minus x. Okay, the mistake that I've seen people make is to say, well, okay, I should sketch this picture by sketching all of the function, right? It's got an asymptote at x equals 1. And when x is very positive, or when x is very large, this is close to 0. And it blows up like this. Whoomph, through that dot. And then whoomph, like this. Y, x. So that as x tends to infinity, the function tends towards 0. And the mistake that people make when they draw this is to say that what they've drawn is the solution. I'm being pedantic. What's actually happened is that your function here blows up to infinity, and then the game's over. This bit is not part of the solution. And if you're not part of the solution, you're part of the problem. No, sorry, you're part of the problem was up here. The problem was this. If you're not part of the solution, you're just some extra bit of graph. When I've talked to people before, they've tended to believe quite strongly, right, that we found this 1 over 1 minus x, and I can draw that. It looks like this with 2 bits. So that's the solution, that's the picture is the solution. But in fact, that's not the solution, or in fact, that's only the solution on a particular domain. The idea is that, well, so this is consistent with the original question up to a point. The whole game here is to find a function which, when you differentiate it, gives the square of its values. And that's just not true at x equals 1 for this function, or it turns out for any function. But this function, when you plug in x equals 1, you don't get a number. And when you square it, you don't get a number. And that's not the same thing. So sometimes people have now tried to argue with me about infinity, or the fact that not a number kind of should be equal to not a number. I don't know how programming languages handle this. If you're into programming and you have strong feelings about this, is it true that nan is equal to nan? Probably depends on language a little bit. I feel like nan equals nan should return false, but I don't know. I'm sure that there exist languages where the question, does nan equal nan, not a number equal not a number, comes back true, which is going to be horrifying to me. I'd quite like it if does not a number equal not a number came back with the answer not a number, or indeterminate or something, but I don't know. Maybe I'll Google that quickly. Does nan equal nan? There's an IEEE standard which says that nan should not compare as equal to itself. But the top answer on Stack Overflow is wrong or something. Great fun. Great fun. The accepted answer is 100% with you. I love Stack Overflow. Let's have a quick look at Stack Overflow together. Here's Stack Overflow. Why is nan not equal to nan? I don't know what language they're using or where they are. Maybe it's everything or something. And then you get answers like this. The accepted answer is 100% without question wrong. Great fun. Nan's supposed to propagate through stuff. Oh, I guess I'm not reading all of this. Good, okay. Right. Anyway, the point I'm trying to make is that at this point here, something's gone wrong. And it's not okay to draw in this bit of solution. Sure, it matches this function, but the game's up. There's no way to get from here on the left to here on the right with this equation being true all the way in between. There's just no way to join things up. So if that's allowed, then, well, lots of things should be allowed. we set the constant to be -1 because we were interested in going through this point, and we've done that. Maybe on this side we could choose a different constant. People generally sort of hate that idea, so I just don't win the arguments at that point, I think. But in some sense, choosing a different constant on this side, everything's consistent over here to the right of the point x equals 1. Everything would be consistent over here if I chose a different constant over there. So y is 1 over 2 minus x or something, although that would be quite a strange choice. Yeah, so everything would be consistent over there, and it wouldn't join up, because of course not. Nothing joins up to the left-hand side. But what people actually say is that the solution only exists on a particular region, which stops just before you get to 1. You cannot include 1 in your solution. Right. Yeah, okay, we're going to do a quite technical existence theorem, are we? I'm reading the notes again. Certainly the most technical thing in the course, the thing that I don't really know. Oh, I don't remember the Weierstrass M test. Oh no. Here's what's going to happen for Picard's theorem, a thing which I'm going to try and learn for the next half an hour. We're going to see how that goes. We're going to look for a solution to this problem. Oh no, the original problem with f on the right hand side. In a rectangle about the initial point. Suppose right, so I'm rectangle. X is only allowed to vary a little bit. Y is only allowed to vary a little bit. H is half the width. K is half the height. A plus or minus H. B plus or minus K. Seek a solution in that. I don't know. Okay, right, good. Let's have a look at the diagram. There it is. It's got height 2K and it's got width 2H. That's a rectangle. So what's f? Sorry, f is the function on the right hand side. We're going to try and solve. There is a dog outside. The dog is trying to join in the live stream. I'm co-hosting this one with a dog. Quite control the dog. Hi Zoe, I'm trying to learn differential equations. There you go. I've got some notes. I'm trying to learn. I'm smiling because I should already know differential equations. I should know them inside out. But there's a big technical theorem that, for various reasons, I never learned when I was a student. I've kind of avoided it since. But my hope is that by streaming about it, I might trick myself into learning it. It's called Picard's theorem, and I can't remember how it works. This is second year of the Oxford Maths course. So if you're coming on the Oxford Maths course, you will do this in second year. Hooray! Yes, thank you to the dogs. Everyone, thank you to us. Okay. They made good effort making the noise outside. Right. We are trying to solve this differential equation. Ooh. Not in Maths and CS, because Maths and CS students don't do as much differential equations. I'm probably not going to look at all of the technical details though, so we're just going to see a thing. Yes, this might be bonus content. If you've signed up for a Maths and Computer Science degree, but you've also tuned in on Sunday, then maybe that's how you get bonus maths content. Yeah, there you go. More reasons to know now. Right. What are we doing? Right, we're solving this differential equation. It's just dy over dx of f. But it's also f of x. So I need to remember that x, because the function on the right hand side could depend on x's and y's, and not in a simple way. If it's very simple, I might separate variables. If it's just some things multiplied by some other stuff, I'd love that because I could use separation of variables. If I see sine x, sine y, I'm all over that. Yeah, divide by sine y, see what happens. Okay, but might not be. Might be some complicated function where the things get added, or 1 to the power of the other, or something like that. Good. Right, first assumption is that the function is continuous. And we're setting up some conditions. There's going to be a theorem, but we're just sort of describing, the lecture notes are describing what to expect when we get to the theorem, I think, is the structure. Here we go. First assumption, f is continuous. I I think so that we can integrate it, probably. There's a first year course about integration. Integrating A like this gives, right, so changing y values because you're integrating the derivative of y. Fundamental theorem is the integral of f across that range for any x. So we've integrated, this thing was dy dx equals f for x and y. So integrating that gives you the change in y over here from a up to some general value of x. There's a dummy variable of t, looks nice. And your initial, I forgot to write down also that we're solving this with the initial condition, y of a is equal to b. That's important. I think it's one-dimensional as, I suppose, as the x is a scalar variable. So I think in this course we're just looking at a function of one variable. Y, which we're solving for, is just a function of one variable, but this function on the right hand side is kind of a more complicated object because it can depend on x and y. So I think we might be doing just a kind of boring old function for y of x. We're on a kind of restricted domain. Oh, so restricting f. No, what are we doing? Since f is continuous and y is continuous, so this function is continuous and so integrable, I guess this exists or something. An example of a function that might not behave like this. So if y is differentiable, this first bit always works, but you might not be able to integrate the function on the right hand side. If the function is horrible, then you might just be able to not be able to decide what value the integral should take. A sort of classic example, and this is mad and maybe a bit too nasty to be the example I should show you, but a kind of classic example of a function that you can't integrate in this sense is to have something that's, so if f is 0 for rationals and 1 for irrational numbers, then you run into this weird problem that you can't decide whether the integral should be 1 because there's lots of rational numbers. So it kind of feels like there's a big rectangle here where the value is 1 quite a lot of the time from 0 to 1 if you're trying to integrate f from 0 to 1. Or maybe it should be 0 because there's loads of irrational numbers in here as well. And on the irrational numbers, it feels like you have 0 up here and 1. So you have this kind of dichotomy, really. But there's a technical definition of integration, a Riemann integrable function, that people learn in first year maths. Maybe maths and CS. No, maybe not maths and CS. There's a technical definition that people are learning, which rules out some things from being, from this integral being defined on the right hand side. That could be quite bad. I don't think anything nice happens for the differential equation if you try and work with this function on the right hand side, because I don't like it. But maybe there's some more advanced theory that lets you get around that. Yeah. Oh, right. Oh, sorry, you want a function for which we're doing something like this. Sure. So, I mean, we might be trying to solve something like dy by dx is equal to y plus x. Or something if I just put a plus sign in for the function of two variables. I've got x and y. So it might depend on, the thing over here might depend on y and x. I think you can solve this using some mix of exponentials and polynomials. But that's kind of not really going to be the point of the course. The idea is just, here's something that you might see at A level. Dy by dx might be x times y, or like x squared y sine x. Which these ones I start to feel like I should separate them, but also there's a whole bunch of other stuff you can put on the right hand side. Sometimes it goes really wrong. Sometimes you don't get a unique solution. So this one I feel like it should have a unique solution, because I think at some point in further maths I learned how to solve most of the things of this shape. It's not that bad. So I feel like this one should be nice. We've seen some examples half an hour ago of things that are a bit nasty, where this pleasant looking differential equation with a 2/3 up there, so maybe not that pleasant looking, has lots of different solutions involving these different piecewise functions. Yeah, I might want to do something like that, some sort of integrating factor. And first year maths has got loads of integrating factors. I have skipped that from the live streaming point of view because there's some overlap with A-level and equivalent stuff, and because I feel like I already know it. Whereas this stuff is stuff that I don't know very well, so I'm trying to talk through it. Yeah. Yeah, you see that function quite a lot. Neutrinos. There's some chat about first year courses. Good, right, okay. We're going to get through this. It's going to be. We've had some foreshadowing that the Weierstrass M test might turn up, and I cannot remember how that works. So, fun. Right, okay, we're planning to differentiate this. This seems fine. Yeah, okay, so we're planning to differentiate this to get back down to dy by dx is f of x and y of x. Using the fundamental theorem of calculus, that kind of integration is the opposite of differentiation. Differentiation is the opposite of integration in some sense. So you can, if you have x up here, you can differentiate that by thinking about how the integral changes in relation to the value of the function. Right, then we now have an integral equation. Great. With a particular case, which looks like this, we are looking for a function y such that when you integrate some horrible combination of t and y of t from a to x and then add on the number b, you get back to the value of y, which seems like more complicated, right? Because it involves integration. And actually, this is the one we're going to work with for Picard's theorem. Here's the framework. There's some successive approximations. The surprising thing, I guess, is that this works, that this gives you the solution to your differential equation. In some cases, there's some terms and conditions on the function f, but I think the punchline is that this works. So you start by guessing that y of x is just a constant function b. You take your initial value. A quick reminder down here again, we're solving dy by dx is f of x and y, some combination of x's and y's, with initial condition y of a is equal to b. That's terrible handwriting, sorry. With y of a equal to b. So first guess, is it just constantly b? And that's a terrible guess. Unless, if your function was 0, then hooray, you have guessed a solution to your differential equation, great news. And then to get to the next approximation, or iterate, I guess we don't know their approximations to anything yet, but to get the next one, you integrate f of, using the previous iterate you had, and add b. And just the hope is that gets back to, gets closer and closer to something that's kind of correct. If these were ever the same as each other, you would now be done, because you would have an example of y such that when you integrate f of t and y, you get back to and add b, you get back to where you started. So if these matched up, you'd be good. I guess if I was trying to introduce this to A-level students, we would probably do this a bit. I would take my t plus y business. So it's my, what did I have? I was thinking about this being x plus y. For one of the easiest functions of two variables is to add the two variables together. So in that case, I would have something like yn plus 1 is a b plus the integral of t plus yn dt. And it's not at all clear that this gives you anything particular. I now realise there's an old maths question that is like this. We looked at it on a live stream before the summer break, on the professional live stream that I do for Oxford, with lots of this repeated integration. In this case, I guess this is quite nice. So I'm going to get, it's getting a bit wound up in itself. So I should get, because secretly I know that this is exponentials and polynomials, it's kind of going to give me, every time you add on t and integrate, add on b. Maybe I could choose for mine. then that's the number 1 or something. So then I'm going to get something here with this t malarkey. It's going to give me x squared sort of term. That's going to give me an x squared sort of term. Oh, I see, but then I'll feed that back in to get a t squared, which integrates up to an x cubed, and then I'll feed it back in, there's an x cubed, which the next time I integrate it, it's a t cubed when I plug it in. I integrate it, I get an x to the 4 from plugging in the boundary values. And then that's my next function. So then it's time to go around again, and this is going to generate more and more terms of a polynomial sequence. More and more terms of a polynomial sequence with higher and higher degree. I think this might be generating some sort of Taylor series for the solution. Why do I think that? Do I think the new terms are unchanging? Do I think the lower terms of the polynomial are unchanging? I sort of want to do this a bit. Proving that Laplace transforms work is probably a separate question. This feels like a healthy thing to do a couple of times. Maybe not now. Maybe if I'm not brave and I set. Maybe if I set the initial condition to be this, so that A is 0 and B is 1. That might make my life easier. So then what do I have to do? I have to do 1 plus the integral of. So my first guess is 1, constant function. Yeah, I think I can do this. T plus 1 dt. So I start off with a really boring thing to integrate from 0 to x. So we'll get something that depends on x now. It will be 1 plus x squared over 2 plus x. And having 0 down here is very helpful for me being able to integrate polynomials. Okay, let me feed that round again. That's y1. And then we get y2. We're supposed to integrate again, feeding this in. What do I do then? So this is t plus, and then I write down the stuff that I've got so far. I'm going to put t plus t squared over 2. And I get 1 plus, and then this is going to be x squared over 2, which I've seen before. This one is going to give me x, which I've seen before. This one's going to give me another x squared over 2, so that's interesting. And then x cubed over 6. So what do I think I'm going to get? I think this is starting to look like... it's starting to be honest, it's starting to look like e to the x plus some sort of x squared over 2 business, isn't it? I'm getting more and more of these terms. Look, here's an x squared over 2, but otherwise I'm getting terms from e to the x. So if I'm trying to solve dy by dx equals x plus y, another way to do this is with an integrating factor, where you rearrange things. This is going to be absolutely tiny, I'm sorry. And then you integrating factor it, so it's e to the minus x on both sides? Yeah, e to the minus x on both sides. So that's that. And on the right hand side I've got to integrate x e to the minus x, which gives me something like minus x e to the x, and another e to the minus x, possibly plus 1, possibly plus a constant. Because the minus signs work like this. When I hit the x, I get minus e to the minus x. When I hit that one, I get minus e to the minus x. And a kind of constant from doing the integration. Definitely did that too fast. Yeah, also did it incorrectly. Not sure. Not sure. Yeah, because this is starting to look like it might be x plus 1. What's my particular integral? Whatever. Okay. Yeah, it's only on board. I seem to be getting the wrong thing. E to the negative x when I multiply through. Yeah, I'm going too fast, aren't I? I should write out that line where I multiply by e to the minus x. integrating factor. I was expecting an x squared because I've got one over here. And because if I put x squared over 2 in here, I get x, which seems good. If I put an e to the x over here, I get e to the x, which seems good. So I was expecting x squared over 2. Why am I not getting x squared over 2? I specifically asked for x squared over 2. Multiplying that by e to the minus x. Oh hey, thanks for the follow, Purple Girl 333567. That's a lot of numbers. Thanks for the follow. We are closing in on our follower. There it is. Bing. Closing in on our follower goal. Doesn't have an x squared over 2 term in the answer, doesn't it? That's a surprise. Because an x squared over 2 would be a problem because it would balance here, but it would also be here. Learning. I should just keep writing down my solution, shouldn't I? I should sort of shut up and write down my solution. Which is this, I think. Minus x minus 1, because that gives me a minus 1, and that actually cancels. Ha. Why haven't I got that? Hi, Charlie. 34711. People have got numbers and usernames, it's great. Oh, shout out as well to Securit, who followed a week ago when I was not live. It's not step, don't panic. We're good. We're not doing step. We're doing some random integration. I've got sidetracked by doing a kind of comparison where we do something with integrating factors, which I've tried to do too quickly, and we also try to find this series of approximations using Picard's method. Well, LaTeX is just great. Everything should be in LaTeX. Look at my handwriting. With handwriting like this, how is it not tempting to put everything into LaTeX instead? Good. What do I want? So why am I not seeing that over here? Maybe I am, but I'm being silly. I was not describe this. Am I up by a factor of 2 or something? No, I guess. What am I doing wrong? Over 3 gives me this over 6. And that's when I started thinking, this is x to the n over n factorial. That's all very nice, but that means I want this, and this, and this. So I thought these were going towards e to the x. Constant part. So if I plug in my initial conditions, then I get C as 1. So I think the solution is this. When you differentiate it, the e to the x behaves really nicely on both sides. And the minus x minus 1 is nice because when you put it on the left, you just get minus 1. And when you put it on the right, the x is cancelled and you just get minus 1. So that's a particular integral. Really smart. I don't know. I think I'm being really stupid right now. You think C is 2. You see, we're disagreeing about the constant. Just don't know what number to use. When I plug in 0, I get minus 1. Oh, I get minus 1 and I get minus 1 and I wanted 1. The difference between 1 and minus 1 is 2. Because 1 plus 1 is 2. C is 2. I should have a number 2 in here. I wouldn't say we're very, very smart. I would say we're very, very ambitious. We're trying our best. For me, I'm miles away from what we can do. Yeah, I know. There we go. We've got the number 2 in here. There's number 2 in here. That changes my expectations, doesn't it? That changes my expectations. Because if I have the number 2 in here, then I was expecting, right, okay. So I got carried away with, because then 2 times e to the x would give me 2 and another 2x, and this subtraction would match up. And the 2 times x squared over 2 would be these 2 terms as part of the 2 times e to the x. And I got 2 carried away by seeing this x cubed over 6. So if I put this through again, they give me a bit more x cubed over 6. It's not unbelievable, is it? That it'll give me a bit more x cubed over 6 if I feed it through one more time. So it's something like y3 is 1 plus the integral of t plus everything you've seen so far with t's in. There we go. So the theory is this gives me one more x squared over 2. Here's an x squared over 2. This is integration from 0 to x. And an x cubed over 6. Yeah, there it is. And then this one gives me an x to the 4 over 24. So it is giving me terms that feel like e to the x, but it's giving me them twice to add up to 2 times e to the x. But luckily that is the correct answer. I resisted it back over here. I resisted it by being wrong for ages. But we got there in the end. There's a 2 in here. I couldn't solve the problem either way. Lesson to self, don't beat myself up, but I was so convinced that I couldn't be wrong twice that I tried to bend the answers towards each other to match, so then I ended up being wrong twice. Good stuff, right, okay. So that's an example where the series of iterations do end up converging. Right, we're going to quickly look at some of the proof, but it's going to be complicated. Oh, shouldn't it be x cubed over 3? Probably, in the end. In the end, I've got 2 sorts of x cubed over 6 in here. Oh, maybe I do agree. Where am I? Oh, yeah, it's over 3. Yep, good. I've only got 1 sort, so I'm going to x cubed over 3. Thank you. Yeah, because it's 2 times e to the x. I can still be wrong, even after I've done my little speech to myself about learning from my mistakes. I can still have more mistakes. Oh, this is very educational. Great. So differences, noting that you are the sum of the differences. We want the series to converge, so estimate the differences. Oh my goodness. Okay, here's a key idea which we're going to turn into maths later. Notice that, whoop, there it goes. The difference is the integral like this. Oh my goodness. Maybe not. So we had Linkin Park are back. That's exciting. They've sort of reformed with new music and stuff. Just a random note for you. It looks quite a lot like maths already, doesn't it? This will need a conditional f is the thing that scares me. Like, we're not gonna set it up properly yet, but notice that. Oh my goodness, here's a key fact or something. Maybe that's all I can hope for today, on a day when I can't remember factors of 2. Maybe all I can hope for is that we get the key facts. The difference looks like this, and you can bound that. It's not so bad. The new one is like this. Oh no, do I need to look up the new singer and stuff? Oh no. I was excited. Now I am cautiously optimistic at best. Right. Why is there an modulus outside? No, I do know this. If x is less than a, if you're integrating right to left, that is silly, but sure. We've had this before on the stream, haven't we? Integrating from right to left gives you negative numbers because it's reading the area backwards. Good-o. We're going to bound that, which involves the following definition. So we want the f's to have something to do with the previous e's, and they do because e's are related to the y's. And these, is it just going to be... no, I don't know what it is. Oh, it's to do with the change in... Okay, down here it's the change in the values that you're putting in. A function on a rectangle. Oh, this is now just a general fact about functions, by the way. It's said to satisfy a Lipschitz condition with some constant L if there exists a real positive L such that this difference, when you put in different values for the second argument, is bounded by the difference in those values for all points like this. That's called a Lipschitz condition, and it just applies to the second argument of your function. Weird. Stronger than continuous, weaker than differentiable. Right, because then we can bound stuff. We can say, aha, the difference in these second variables, the y values that we're putting into the function on the right hand side of our differential equation, the change in the function hasn't changed very much, so the values of those functions on the right hand side hasn't changed very much by the fact that when you have a different, so we're kind of calculating a sequence of functions, and our functions go to different places. They have different values, which means they see different values of f of x, y, but not very different values of f, x, y. Is the idea that if you change that input to f just a little bit, then it shouldn't really change too much, or it should be something to do with how much the function itself changed, which you could then integrate to get some sort of bound. Oh my goodness, what is this? Yes, we're pulling in a random condition. This is going to be one of the terms and conditions on f, I suppose. There is a very big "it turns out that" in the middle, which, yeah. So this is different from continuity. It's stronger than continuity, which means that there are some continuous functions that don't do this. Because you can be continuous but have points where the difference like this is extremely large. For example, x plus root y. I don't know why we've got these x's in. They're not really doing anything, so I'm just going to throw in x plus. Well, maybe I won't bother. Maybe I'll just say f of xy is just root y. Or y to the 2/3, crucially, doesn't do this. It's continuous on 0 out to 1 or something. Root y is continuous, but there's no number L such that whenever you choose two numbers to put in here, two different values. On this graph it's y, which I know is weird, but whatever. There's no number L such that when you put in two values, u and v, the difference is bounded by the difference between those values and a fixed constant L, because if I make u and v very close together but very near the origin, then very near the origin this function is very steep, and so the difference there, even if u and v are very close together, even if this thing's very small, the difference between those f values might be much larger than the difference between the u and v values, and there's no real positive L that I can put in to make this inequality true for all u's and v's at the same time. It's sort of like the fact that the gradient is unbounded there, but a function doesn't have to be differentiable, so it's not quite just a function. It's not quite just a fact about derivatives. If your function is differentiable, then you should probably look at the derivative, but if your function isn't differentiable, you have to do other stuff involving this condition. If you make L like a bajillion, then I have to move. It's really sneaky, but I have to make u and v something like 1 over a bajillion squared, or something like that. So that the difference between u and v is tiny. It's 1 over a bajillion squared. But the difference between the y values through the square root is surprisingly large. It's only 1 over a bajillion. And now these things start to look the same size. But I have to really go close to the origin. The bajillion squared account to come. There's always a bigger number. You thought you'd name the biggest number, and I come in off the top rope with a bajillion squared. Well, in this case, 1 over a bajillion squared. Good times. Right. I feel like I've seen this in... Where have I seen this? There's another course where this has been a kind of key idea that I've not really explored, because I don't really get it. I should probably have an example, of a function that's not differentiable, but still doesn't do... Oh gosh. It's weaker than being differentiable. So I think any function that does this... Oh, what's this sequence? There's so many of these things in maths where A implies B and B implies C, and I just can't keep them in the right order in my head, or think about what a counterexample might mean for the second but not the first, or something. In Galois theory, we had a lot of Euclidean domains are principal ideals, but not the other way around, or something. Thanks for the follow, Jeff C. Groves. Thanks for Thanks for the follow. We are close to a follow goal, so it's an exciting time to follow the stream. If you follow, then I think Twitch tells you when we're going to do these. It's 2 p.m. on Sundays, UK time, but not every Sunday. It's quite irregular. Yes, there you go. There's another good counterexample. I don't know what that means. You've cheered bits. We've never had this before. A new animation. Does it stay forever? Oh no, it's gone. And Mary says it's tea time. So wow, what a day. Jeff, thanks. I don't really know what bits are, but I now have some shiny things happening in my Twitch. The thing with all the numbers is telling me some new numbers. What a happy day. Sometimes we do, yeah. Oh, look, you get a little symbol. Yeah. Oh, is that a 3p? Thank you for the threepence. I was going to go and look it up. I suspected that it was about threepence. 3p is enough to get you bit leader in this channel. We will do a maths question. You can put it in chat if you like. We'll have a look at it. The odds are that I can't do it, but somebody in chat might be able to do it. That's what's happened before. And then in a minute, I am going to go make a cup of tea because Mary says I have to. There you go. I do my best. Is that exactly 6? Right. Oh, great. Yeah. Yeah, apparently it costs 3p to get my attention, which, until something else gets my attention. Right, good. Okay, no maths question immediately. We've got the definition of Lipschitz we've got a Lipschitz condition. It's going to let us bound some error terms, prove that the series of functions converges. But it's time for a break and a cup of tea, I think. So I'm going to make a cup of tea. I write terrible code that sometimes gets the job done. Other people in chat are pretty good at that. We're not good at. As far as I know, we're not great at coding questions. I shouldn't speak for chat, I suppose. I would not ask me coding questions. But I don't know. We've got some computer science sort of people. Zoe, look. Zoe has told you about the unofficial Discord, which is in chat. Or not. Yeah, good. Right, okay. I'm gonna make a cup of tea because Mary says that. We're gonna run an ad break. The ad breaks support charity. They tend to make about 3p. So thanks for watching adverts. If you see any adverts, you're helping. We will be back in a moment. If I remember which buttons to press. This one. And that one. And right, it's 3 buttons. 1, 2, 3. Yes. Are we back? I think we're back. Oh gosh. Yeah, that was a longer ad break. Longer ad break. Or longer break than I meant. What's chat been up to? Some 15 and 30 seconds. I've got 4 adverts. Good. No more fancy cars. Brilliant. Yep, okay. Building a computer in chat. Yeah. Oh yeah, me. Hi, I'm here as well. I'm joining in. Are we building a computer? Good. Okay. There's sort of 3 conversations going on in chat. I don't know how you all manage. How do you do it? You've got like 3 threads going all at once. I can only focus on at most one thing at a time. I mean, you've seen. Sometimes can't even focus on that one thing at a time. 2 is definitely bad. Right. Okay, let's go. Yes. So this is going to be a note to tell us that if it's differentiable, then that's kind of good enough, right? If you take the y derivative, if that's less than or equal to some k, then you're good because the mean value theorem is in there. Yeah. What's the name of the actual Batman villain? Possibly played by Arnold. I can't remember. Is it from the 90s? Anyway. That's it. Thank you, Mr. Freeze. Is it was Mr. Freeze played by Arnie? The temptation just go and look up Batman villains. Anyway, it's a classic example of me not being able to do 2 things at the same time. Good. Yeah, differentiable is good enough. And here's an example which is not differentiable but is Lipschitz continuous. Oh, no. Okay. So I should be thinking about how root x. Maybe I shouldn't have root x. So this function, maybe I should ban 0 as well, so that it's actually differentiable at 0. So if I have this, that's an example where it is differentiable, but not Lipschitz. And this is an example down here, which is Lipschitz, but not differentiable. So they are different. Right, good. Oh, Jeff's back, or rather I'm back from Jeff's point of view. There we go. One of my fears is that I'll forget to unmute when I come back. I guess forgetting to mute would be worse, but forgetting to unmute is the one I've got a fear of. So just come back and just sort of carry on mumbling away to myself in the spare room here, just mumbling about mathematics for nobody. Is this real analysis? Says Megalomorph. Yeah, that's what we're doing. Real analysis. We're trying to solve differential equations. I guess. Yeah, I guess that's a form of analysis. In particular, Picard's theorem tells you about solutions without actually telling you what the solution to a differential equation is. So if you're a kind of applied mathematician like me, and you would like to actually have solutions to the differential equations, well, this tells you that maybe you're on the right track. You're asking a good question, but it doesn't tell you the answer to that question of like what's the solution. Right. Yeah, and so yeah, I agree. I should go back a little bit for Zoe's point. So this thing is Lipschitz continuous, but is not differentiable. So you have continuous functions. And stronger than being continuous, because you have continuous functions. So you have this big set of continuous functions, and then all of the Lipschitz functions are continuous. Because if they had discontinuities, then you'd have this big jump, and you wouldn't be able to say that the gap in values was bounded by anything to do with the change in x values. So discontinuous. That's not the only way to be discontinuous, but like inside here you've got these Lipschitz conditions functions, and then I think differentiable functions lie inside that, or maybe overlap with it somehow. Let's have a think. So here we've got something that is Lipschitz continuous, but is not differentiable. So that might lie kind of inside here, but not differentiable. And here I've got something that, oh gosh, is differentiable. What's my example here? It is differentiable, but it's not Lipschitz. Oh dear. If I cut off 0. I'm supposed to be on a rectangle. I'm not allowed to do this because I have to be on a rectangle, which actually includes the endpoints. So this function I think is not differentiable because it's got infinite derivative over there on the left. Okay, so I thought this was an example of a differentiable function that's not Lipschitz, but actually it's not on a rectangle, so it doesn't count as one of the things. Yeah, it is a subset, I think. And the thing that I thought I'd found that was inside diff but outside L doesn't actually work. Yeah, x weaker than y should mean that y implies x. So you should, as Zoe is doing, you should try and stop the stream if it appears to be the case that the streamer has just said that they have an example of not y and, sorry, they have an example of y and not x. You should stop the stream. Good, right. I think they're insisting a rectangle's closed. I think we had a definition of a rectangle. Second year maths, here's a definition of a rectangle which includes all these kind of square brackets and these things on a rectangle. So I think it's this with these less than or equal to signs. So I think that, I don't know if that's important, but it kills my example. So I suppose it's important to me, I suppose, that fact about, fact about what a rectangle is kills off this. No, it's on my counter gambit. My counter gambit is still fine. This is still an example of a function that is not Lipschitz. It just turns out to also be not differentiable. So it's out here. My function is actually out here somewhere. Outside D, but crucially also outside L. I thought for a moment that it might be outside L but inside D, which is impossible, I think. What's the proof that it's differentiable? No, what's going on? What's going on? Am I seriously claiming that all differentiable functions are Lipschitz? Yes, I am. You need the derivative to be bounded, but it will be because the different. I think we're good. Yeah. Can you have a parametric equation that is differentiable in ILC? I don't really know what it means for an equation to be differentiable. I suppose it's the easiest way out of thinking about that one from maths 2 to 2 to 2. A parametric equation that's differentiable. I suppose differentiation is something you can do to a parametric equation. Maybe you're imagining each side as a function of the parameter, or yeah, what's the input? Anyway, here's Picard. Is x squared LC? These are good questions. Is x squared LC Lipschitz continuous? Yes. You have to define it on a rectangle. So x squared going out to infinity has got a kind of unbounded gradient. But if you pick a bit of it on your favourite kind of range, so maybe between 1 and 5 or something on your favourite range, then it's true that any 2 points you pick on that parabola, the change in the y values is not too much more than the change in the x values, because the change in the y values is at most 24. It was bounded by the gradient if you make the points very close together. Is that true? Yeah, it's bounded by the gradient, which is at most 10 in this case. There are functions which are differentiable everywhere, but not second differentiable. There's probably a function that's differentiable everywhere, but second differentiable nowhere, because, yeah, that is probably the sort of thing that exists. Yeah. The hard version is to do it. Bad stuff everywhere. Okay, good. Right, we're playing with all the kind of good examples and counterexamples. The more of these you think about, the faster you gain intuition about which things imply which other things. Good stuff. Yeah, and Jeff wants to integrate a function. It's not obvious you can integrate. Well, I guess if it's continuous, you can. So yeah, integrating continuous functions is not differentiable. There exists, I think, examples of continuous functions that are differentiable nowhere, like that Blamonge-Weierstrass thing, Blamonge-shaped thing. So if you integrate that, then maybe you'll get something that's continuous differentiable, but second differentiable nowhere. That might be fun. Don't do that. There's that kind of people not being happy about piecewise functions, which I think is fair, but some of them aren't as bad. Weierstrass is what you're thinking of for an anywhere. Good, we're on the same page. Okay, here's Picard's existence theorem. It's going to tell us when we can solve differential equations, or at least when we can get unique solutions for differential equations. Turn that back to that. Here's a function defined on the rectangle, so with these less than or equal to sides. That's a definition of a rectangle as well, so that's nice. And it has to do these. F is continuous in R with bound M. So continuous functions on a closed interval are bounded. So here's give that bound a name. And they want it to the absolute value of F is bounded. Fine, okay. I guess continuous functions on a closed interval are bounded above and below. Take the larger magnitude of those. Fine, okay. I believe that this M exists because I know some facts about continuous functions. And you also need which satisfies, I'm in the middle of a sentence, look, which satisfies MH less than or equal to K. So what's this doing? Oh, we're going to think about this being some sort of derivative of y, and we're trying to say that the derivative is not too big. Something to do with k, the height of the box. And also f needs to satisfy a Lipschitz condition in R. Doesn't matter which one. That seems fair enough. Doesn't matter what the constant is. Then the IVB has this with the unique solution and you get all the way, you get a solution for all of these values. So this looks restrictive because we're only solving on this little interval, the kind of range of the rectangle. But the proof is going to show us that this thing has values in some particular range, and it's a unique solution. So kind of multiple things going on here. The fact that it has a solution is interesting, because we've seen examples where this thing blows up or just, there isn't any function that does this at all. The fact that it's unique is interesting because we've seen cases where there's multiple functions that might do the same thing. And the fact that it's on the values lie in a particular range is also interesting because we've seen these things get extremely large as they blow up. I made him Morpheus off doing 5 hours of tutoring. Gosh, good luck. There's some more chat. Maths wants to know about Maths 2 to 2 wants to know about t minus sine t, 1 minus cos t. Oh, I see what you're doing. Sorry, right, got it. Because you're trying to do something a bit like this. That's something where both functions. I'm not sure I've sketched it right, but maybe you're doing something like this, where both functions are continuous and differentiable function of t, but the actual shape you get is not good as a function y of x. Maybe that's what Maths 2 to 2 is trying to do. I'm not totally sure. Have I even drawn that right? I think I have. I've drawn it upside down, but still, I recognise that function. Yeah, okay, so then you've got an example where these functions are continuous and differentiable and very nice functions of t, but the shape, if you trace out coordinates x of t, y of t, the shape's not nice because it has these sharp corners in. So I guess it might be the case that as you change t, the point that you're talking about doesn't change very much. So the function from t to x, y or something might have a Lipschitz condition, but then the shape, so we're drawing these shapes on the screen, and the shape y as a function of x might not have a Lipschitz condition. As you change x a little bit, well, that involves changing t in some quite a strange way. Possibly. Yeah, good, okay. And there is a way to differentiate those to try and convert between the derivatives. Good. Okay, so we've got several observations about what we get out of this. And the key thing is that we've got to make sure that, so using this thing that we've just learned about Lipschitz conditions, the key properties, I think it's a P for properties. Anyway, key properties are that it seems to be continuous and bounded, but there's this, and not too large, fine. So this bound is just to stop it getting outside of the rectangle, I think. If this didn't hold, then maybe your derivatives on the right hand side here, your f values for dy by dx would be so large that the function would be large enough to escape out of the box. You know, in a distance of h, if its values were as large as m, it could maybe grow as large as mh. But if you keep that a little smaller than k, then it's sort of not surprising that this thing's bounded by. This last bit about the values being bounded, well, you told me to make sure that the values were bounded in here, so that's the values of the derivative, and now you say the values of the function are bounded. I can kind of see that follows through. You can see why you've done that if you want this result out the end. But there's also a thing about Lipschitz conditions in there, which I suppose is going to be so that the things converge. Right. Yes, here it is. I should just, almost always, I should just read the next sentence in the lecture notes rather than try to guess what's going on. Converge to a solution. Show that the series in 1.7 converges, the thing we were doing. And that's to say, claim 1, let's look at the structure, but each line is well-defined, continuous, and doesn't get too far away from where you started. Inside the rectangle, I guess. Like that. Okay, that seems plausible. We're just doing some integration. It sounds nice. They don't get too large or whatever. Fine, okay. Claims true by induction. I'm skipping the proof. And then these differences between them are bounded by some geometric series. So that's good. And that's going to be something like, bounded by a geometric series, and this x minus a to the n is good as well. So in particular, well, x minus a can't be that large. It can only be as large as h, so these are really small. We're going to be able to add all these errors together to get kind of something about. Okay. Oh gosh, there's the M test. Okay. So this claim looks like it comes out of nowhere, but remember that these e's are defined as the difference between f's, difference between y's, and difference between y's satisfies a differential equation involving the f's also satisfies an integral equation, if you like, involving f's again. So it's not too surprising that you can get from a statement like this, if you know about difference between f values, that's the thing in the definition of Lipschitz condition. The Lipschitz condition says that this difference between the f's, the whole point of setting up the condition, I suppose, was so that we could say that this difference here, you're changing these values u and v. Well, the difference should be something like less than or equal to big L times the difference between these values. And the difference between those values is just called En. So if you like, it's the perfect sort of condition if you want to get from this kind of tricky expression involving your function f, if you want to be able to say that that's, not equal to something, but bounded by something involving some constant. I don't really care what the constant is, but some constant involving the change in the y's. If you want to do this step, then Lipschitz condition is kind of the correct thing to be doing. To say, what I really want is that this be something to do with that error, that change in the y's. And it brings up the factor L, but I think we don't care about that because this thing's going to converge even with big L in there as well, probably. And then something by induction. Yeah, we're going to skip the rest of this proof. Test out this. How much do I believe this? If one of it was true, it's induction. So if it was true for one value of n, then just integrate it and see what happens. Good. Okay. Claim 3, the iterates converge uniformly, which, good times. There's a definition. There's a definition for that, but I think I can remember. To a continuous function, and that one is the solution of the integral equation. That's 2 claims. How does this proof work? We're going to skim it together. It uses the Weierstrass M-test, which I can't entirely remember, but I'm reluctantly putting off the Weierstrass M-test and uniform convergence, I think, until another day when I go back and relearn what the Weierstrass M-test does again. I think I've learned the M-test 3 or 4 times in my life. It doesn't stay in my head. I'll try and find a way to keep the Weierstrass M-test in my head. If anyone's got any good tips of how you can learn something that you want to know and then continue to know it, if anyone's got any good tips in chat, let me know. How do you retain information? Good, okay. Chat engagement, there you go. How do you retain information? It sounds really like I'm an alien trying to talk to humans, doesn't it? Hello, humans. How do you do this thing where you learnt a thing and later you know it? It's very strange. On my planet, we learn things and then immediately throw them away and have to read them again if we want to know them again. That's not how humans talk, is it? Ooh, Supremum, love that. This thing's going to 0, so apparently everything's fine. And this actually satisfies the divergence equation, which is pretty good. And then there's a uniqueness thing, which is just going to be to look at the difference between 2 of them and do the same bounds. Subtract them, bound it, but then say this thing, that's bounded as well. What's going on? Oh, induction, and that's going to 0. Oh, it's a very exciting proof. Okay, right, I like it, but which bit of it am I going to try and understand? What's going on here? What's really going on? It's that bit with all of the bit where the L's don't matter because the thing is going to 0. That's the bit I don't remember. If you forgot about it, it probably wasn't important. That's problem don't. And I like Neutrino's point about there isn't a problem with relearning things. I guess that's what I'm doing. I knew some of this at one point, I think. Started to think maybe I didn't know this at any point, which is different. See you, Zoe. I don't have a sign off so much as good. Congratulations, you're now the bit leader. You donated slightly more than 3p to the stream, which eventually ends up going to charity, so thanks for that. Good. What am I going to look at then? I think I want to know about this claim 2 business. Just because it feels neat to learn about Lipschitz conditions and then actually look at what's going on. No, I need to reclaim 3. This bit is just pulling out factors of L. So I feel like I'm happy with this bit because it's just pulling out the factors of L and some definitions of the error terms. It's down here where... Down here. This thing's bounded. Yeah, so let's try and understand this induction. That'll be a good step, I think, towards understanding what the hell's going on here. The function's bounded. That's one of the conditions that we put in there. There was something else about k, but that's not relevant right now. mh is less than or equal to k. That's not relevant right now. This thing, when you integrate with absolute value signs here and around here, the ones outside are kind of just to make sure that to cover the case where x is less than a, the ones inside are because we're integrating absolute values. Oh, there's an inequality here. So the error term is defined as something to do with the integral. Yep. The error term is something like defined like this, because E0 is actually equal to, we define this to actually be equal to B. In the beginning there was one guess that the function was constant. Why not define E0 to be B? Okay, previous thing was nothing, I guess. Yeah, I've overthought that, moving on. So then we're integrating this. Oh, so we're integrating this as if it's a... This is silly, but I just need this line in the middle, I think. With mod size around the outside. Yeah, because this thing, the thing that we're integrating is bounded by m. So I can put m in there, and then I can do the integral. I think that's 2 steps for me. There's no shame in that, but I think for me to understand this, I need one more step in the middle. The lecture notes take these big steps, bam, 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 and I'm scampering along trying to keep up, and I have to take more steps than sometimes the big steps that are going on there. There's no shame in that. I've just got little legs, and there are other points where I feel like maybe I can skip steps so that I can see what's going on. I can't see any on this page, but I'll let you know if I find any. Okay, so induction says true for n, then the error term is bounded by something like this. And if we had this thing with the kind of jumping to the answer, right? Because we have this induction hypothesis to put in all of these L's. And you get exactly one more L, but you still have to integrate this. It depends on X. So when you plug it in, it depends on T. There are some mod signs because we're doing the absolute value of that. Something to integrate, isn't it? I'm a tiny bit surprised that I can integrate this with all the mod signs on, but I guess there's only really 2 cases where X is larger than A or when X is less than A. These numbers, T minus A, will either be positive all the way through or negative all the way through. In either case, we can do some integration. Cool, and you get one more factor of L. We started with none. One more factor of L. You keep a factor of M, which you got from the start, the original bound on F. You get these things which depend on X minus A, which is kind of cool. Get larger. This kind of error in how we're approximating the solution might get larger as you get further away. We're hoping that this stuff converges. That's all right. Divided by n plus 1 factorial, because that's kind of defining, there's this polynomial growth of the nth term. So divided by n plus 1 factorial. But I guess these are the errors. We're going to add these together. Maybe it is almost time. 25 minutes on the clock. Almost time for me to learn the M test again. Okay, I think I now accept that. This looks pretty scary, but it's trying to explain the way that well, this integral definitely has to depend on X minus A in some sense. If X and A are different, then you get, if that's larger, you could totally believe that that error works out being larger. You're just integrating more stuff to do from previous error term, which, if you're integrating a non-zero function over a longer and longer range, you might get more and more stuff. So that kind of makes sense that I could grow with X minus A. Yeah. Oh, right, yeah, so I was worried about this as well. In general, I think that's hard, and you have to worry about integrating across 0. But for us, there's a relationship here between what we're integrating. So we're integrating, the limits here are going to save the day. So if you're integrating, so you've subtracted A from both, so I'll do the same thing. If you're integrating like this, oh, whoops, let's not do that. Let's not change variable, actually, because we've got an X up there. There are actually just 2 cases. If X minus A is positive, and if X minus A is negative. Because if this is positive up here, then all the values of t that we're putting into this integral are positive numbers. So we just get this, which is nice. And if there's negative numbers, then all these things that we're putting in are negative. So we get minus 1 to the n out here. But actually we're saved by having these large mod signs around the outside as well, which then mean that we don't care about any number of plus or minus signs. So there's kind of technically 2 cases here. Each of them is then easy to do to integrate t to the n. But we're saved by having some more mod signs around the outside. The tricky case is something like if you had to integrate minus 2 to 1 of x mod x to the n dx. That one's a bit harder, because you'd have to split up the integral. It kind of contains both cases, like this. Plus, and then from 0 up to 1, you have to remember mod x is now just x. So I've kind of got these 2 cases where I've got minus x this thing with the mod signs behaves like minus x for negative numbers and positive x for positive numbers. So maybe I just had to split them up, but here I'm lucky that I'm integrating from a, which is the point where I might have to start thinking. If you put a and hit a minus a at 0, we all know. But luckily this range of integration doesn't cross the scary point. There's maybe something in that. You could mod signs look really scary because they're inherently a kind of case-based thing. So the positive or negative is a kind of piecewise function, but you might be mostly on one side of the case definition. So that'd be good. Okay, so I think I've kind of accepted this myself. A bit weird that x minus a to the n plus 1s. Yeah, they're just weird. I'll take that. I wouldn't have guessed that, is the thing that I'm thinking, I guess. I wouldn't have guessed this. So proof by induction is a bit magic, right? You kind of need to know what you're doing before you do it. Sort of need to know what the answer is in some sense before you prove it, because you want to assume the base case. You want to assume the previous case to prove the next case. So unless you've spotted the pattern already, it can be quite hard to set up your proof by induction. I guess I work out a couple of these and I noticed I'm always getting more factors of L, and this x minus a stuff is taking over. Oh, and then final step, sorry, that's bounded by H. Kind of cool that we don't, why don't we just bound it by H individually for each error term? Because then we'd integrate the next one and we would get a factor of H. Yeah, can't we just bound them individually? If you only care about that, why do I want the x dependence? Why do I have to keep that? Can't I just say, induction hypothesis, this thing, if I write h to the n here, it's worse. It's worse as a bound because I have h to the n. But that's a constant. I would much rather have a constant, and then I'll get an x minus a, like I did in the first case, which I'll replace with another h. And if I'm going to switch it up to h to the n plus 1 anyway, I feel like I've been forced to integrate this function and have this chat with maths2to2 in chat. Maybe for no reason. It's cool. It's a better bound than just saying h to the n plus 1. But I think we're about to say h to the n plus 1. Maybe not. Oh no, we are. Yes, we are. There it is. But this says uniform convergence. What are we doing here? What are we playing with? So is the M-test one, judging from context, the M-test is one where you compare it to a sequence that's geometric and you know it converges. I can't remember what the M's are for. Right, so not proud, but it's time to learn the Weierstrass M-test again. Here we are, once again, me and the Wikipedia page for the M-test. Right, suppose this is a sequence of real valued functions today, please. Let's say A, and there's a sequence of non-negative numbers, right? Sequence of non-negative numbers such that each function is bounded, those are the MNs, and they converge. Right, so the sequence of M's is bounds for the functions, they converge. And the series, for adding up all the functions, converges absolutely uniformly. Brilliant, okay. You get uniform convergence. Maybe I'll remember it if I look at the proof quickly, because then there's more stuff in my head to do with this. Maybe. Oh gosh, yeah, okay, hang on, I'm around about here. There's a difference between the partial sums, it involves these. Oh no. Yes, rings a bell. I'm going to try and stuff all of this into my head so that I remember the condition. It's not working. Fine, look, whatever. Okay, good. Another time. Is this relevant right now? Can't see how it's not relevant, right? We've got these bounds on each of the functions, but I'm suspicious. We now seem to be talking about functions as functions of x again. It's just true at all values of x, right? So that's genuinely a bound on the function. What am I missing? Maybe I'm not missing anything. It's just sort of, we have this nice bound that depends on x, whereas in here we take a bound for each function because that's how the m-test works. So the functions converge. I guess it's the functions that are converging, not constant bounds for the functions that are converging to y infinity. So maybe that's what we're doing. Okay, maybe I should keep these with, I think, x dependence in, because those are going to converge to a limit, and I don't want that to be... no, they are though. They're just good. I can't see any more m stuff coming in later, so I think this is the point anyway, that these error terms converge, and by definition they add up to the last one, yn. It's continuous. It's the uniform limit of continuous functions yn. This is something I definitely should go back and learn. But now I have motivation to understand it. Maybe that's what I'm missing. I go and look at the hard stuff. I think, oh gosh, don't understand this because I don't understand the m-test uniform continuous limit stuff. And then I can go back and understand it better. Yes, I would love to exchange the limit, and yes, I'd love to exchange limit and integral. Is that just something that I'm allowed to do? With supreme, oh my goodness, I guess I should learn the definition of integration or something as well, so that I know that it's okay to swap integration and limits in this case. Star here. Right, okay, so supremum over the range for the difficulty. Sorry, I know this is not very interesting anymore in terms of TV. We will get back to doing something fun in a second, I guess. Good. Yeah. Okay. Oh, so it solves the integral equation, so it's good. Yeah, so you create a sequence that is larger than yours, which converges, but there's more to it because the convergence is happening uniformly. So part of it is that you're replacing the functions with constants, so that you know that. Part of it is that you're trying to say that it's converging everywhere at the same time. Maybe we should think about uniform convergence instead. It's something we can get more involved with, isn't it? So uniform convergence is a way to get around this problem when you're talking about functions. If you have a sequence of functions, there is some weird behavior that you can have where at any particular value of x, the function is settling down. So here, at this particular value of x, the value is non-zero and then very small and then basically 0. Over time, it's converging. There was some sort of behavior as well. Over here, the value of x is very, very small, and then it's non-negative, it rises and falls, but then it tends down to 0 afterwards. So there's some transient behavior where the value at this value of x, the value of the function at this value of x, rises and then falls, but then it converges to 0. And this is weird because you get into this situation. Maybe you noticed my function for each value of n is just moving to the right. So it's creating problems further down the number line. This gives you this weird situation where for any particular value of x, the function will eventually converge once this wave-like shape has gone past. But overall, you can't say that the function is closer to 0 than it was before because it still has this lump in. Somewhere the convergence hasn't happened yet. Somewhere the convergence hasn't started yet. So this is an example of a sequence of functions where for each point the value converges to 0, but the distance between this and the 0 function is non-zero. Kind of almost however in any sensible way of measuring the distance between this and the 0 function, this is not really getting closer to the 0 function. So is that bound for the whole? Create a sequence that's larger than yours, which converges. Bound for the whole function. Yeah. So it's bound for for each of these. The Weierstrass M test gets around this by saying, if it were the case that these functions individually, there's also a sum in there for the M test, so maybe we shouldn't go to the M test just yet. It's about summing these things where you're trying to add some stuff together. So maybe we shouldn't go just there yet. Do I want to do a sum? Maybe I do. The sum is kind of crucial here, isn't it? Because we have a sequence of functions constructed out of differences between pairs. For whatever reason, we've introduced these E functions, which are the difference between Y functions. So I should really try to learn the facts about the sum of infinitely many functions. And that could be problematic if each of these functions that I'm adding on is difference between the errors, right? It might be fine for most values of x, but causing some problems somewhere else. And I don't want it to be the case that as n goes to infinity, I'm just moving my problems along to moving the problems into the corners of the room or something. If you're trying to put down carpet and you're putting down the carpet and there's a bump in the carpet, it's a metaphor that people use quite a lot. You're putting down carpet in a room and you're trying to get the carpet to fit, and you push the bump down in one place and it comes up in another place. You push it down there. You don't want that for like your function of carpet distortion over time as you keep iterating. You don't want to just sort of solve one problem, create a problem, solve and create. You want overall things to be getting better overall. Wrapped up in the idea that we're summing things together, we're adding, each time we're adding on some more function. Painting a wall or something. Yeah, that's the idea. So the sum of the functions will be less than the sum of the functions will be less than the sum of the maxima. Yes. And if that converges, then the sum of the functions result is converges uniformly. Uniform convergence means, well, sort of the same as convergence, but for all points at the same time. So convergence normally says, for your series of functions being added together, a series of numbers being added together, then if after a certain amount of time you're close to the target value, for any value of close, you can find a sufficiently long enough that it happens. And uniform continuity adds in the word everywhere when we're talking about functions, to say if for all epsilon you can find me an n such that after that point the two functions agrees with the target that it's converging to for all x everywhere forever onwards, then we're good. Epsilon, delta, blah blah blah, but it's one of those ones where it matters. It matters what order you have the quantifiers in. You can have kind of there's this kind of difference between let's try and do it then. Okay, so there's kind of, you can have this for all x. So you have this kind of continuity definition, right? For all epsilon, there exists an n such that the sum for up to such that the n. We can do this. Here's a little sum convergence of a sum definition. For all epsilon, there exists an n such that for all n greater than or equal to big N, the sum of the first n terms, after you get that far, of these terms, differs from the target that you're going to by at most epsilon. And then there's kind of two ways that you can make this to talk about functions in here instead. So if you're talking about functions instead, such that there exists an n, and then for all time after that, the sum of your functions looks like your target function, its difference or something. So I suppose I need to put in here like the, well, it depends what you want to do, but let's put in the supremum of the difference between these things, the maximum difference between these things, if you like. Supremum technically, sort of maximum distance between these things less than epsilon. You should put for all x in here somewhere, And the correct place to put it if you want to do uniform convergence is here, kind of inside some of the brackets. So epsilon delta blah blah blah, but oh no, it kind of matters where you put the x. The wrong place to put it is right out the front. Just say for all x, thing converges. That gives you one sense of convergence, which includes my sort of travelling wave example. If you put for all x outside over here. For all x, it's true that whatever epsilon you pick, there exists an n such that after that point onwards, the supremum of the sum of the functions at that value of x is less than or equal to epsilon, or less than epsilon. That's the version that includes stuff like this. So you would say, that converges in the second sense. But in this first sense, where the for all x is kind of buried inside, to say, no. You have to pick a big N such that this happens for all values of x at the same time. That version is called uniform convergence. And it's harder. So that in the uniform convergence sense, this series of travelling waves doesn't do it, because, well, whatever n I pick, the wave is still hasn't yet reached those values of x. So there's still some problems coming up. Still some bits where it hasn't converged yet. I guess I wasn't really talking about a sum over here, was I? But maybe these are the functions I'm adding. The functions I'm adding are the differences, and these are the sums or something. I'm being quite vague, switching between functions and sums. Okay, so maybe this is where I should be looking next. This kind of subtle difference between convergence and uniform convergence. If I want this function to converge, if I want this sequence of functions to converge uniformly, and at some point I'm going to have to learn the Weierstrass M-test. So maybe this is a job for a future stream to go back and relearn those things. Yeah, Maths2 would like to use open sets continuity. Fine. There are many exotic sorts of open sets that you might define when you get to kind of functions, right? You can define lots of different metrics that you might want to get in there, or even not at all. Just choose your own open sets. Anyway, I think this is a good point to wrap up, actually. Let's have a quick look at Picard's theorem at the end, just sort of appreciate what's going on as a kind of existence theorem here. If you have this kind of Lipschitz condition, then you can do, it's kind of incredible, it's almost a kind of constructive mathematics way of actually solving this thing. You can construct this sequence of approximations and prove that they get better and better. And they converge to something that actually solves this differential equation. And along the way, work out that your solution, well, therefore exists and is unique. And I think the side note, this thing is bounded as well. It stays inside the box. So this is all, I think, pretty good, and I should try harder to understand it. It can rule out things like this weird behaviour where you have these piecewise functions you wouldn't have thought of. It can maybe take quite powerful, because I hadn't really appreciated all this stuff with integrating factors, which we made so much mess of an hour ago. But all this stuff with integrating factors is of this format. It's an ordinary differential equation. I kind of knew that, but I hadn't written it out with the function on the right hand side. So maybe I should do that more. And think about some other examples where, I don't know, presumably this one is nice and this one is not nice. But, you know, we should think about which way around. It seems like x and y are treated quite differently in these theorems we've seen so far. So it changes in y and changes in x. And y over x seems probably fine, right? X over y, probably quite bad. So maybe those are the two examples that I should think about as homework. Cool. Okay, I don't know if we're going to do this again in the future or if we're going to do something else and different. If you want to go back and find out what's going on, then you might like to look up Picard's theorem or uniform convergence or Weierstrass M-test. Or, to be honest, I think the thing that I'm going to take away probably most from this is the thing most similar to stuff I do remember, which is the kind of iteration stuff, that you can solve these differential equations by iteration, and maybe that'll help me understand why it might be cool to prove that that iteration actually works. Okay, it's been a live stream. Try to work out how Picard's theorem works, so I can say something vaguely intelligent about it later in the week. Thanks for joining in. I don't know if I'm here next week. I'm visiting. So I'm out in London. I'm just visiting people in London for a part of next week that maybe includes stream time. I might not be live. It's hard to say. I don't plan my life out that much. Who knows? Maybe I am here and I just stream anyway. We will work it out. Good. Right. Okay. Check their stream schedule on Twitch or something. And Guinness. Thanks to people who followed live. We gained 2 followers, did we? We gained 2 followers. I think it's 2. We're now at 209. We're so close to the cube number of 216. We had a square number, now a cube number. Oh. Right, good. Okay. Take care, everyone. See you around. Remember, be careful with your differential equations. Bye. What a sign up. I'm ending the live stream now.